Hello friends, welcome to my lecture on simplex method, the first lecture on simplex method. When we solve a linear programming problem by graphical method, we notice that the region of feasible solutions is a convex region. It is bounded by vertices and the edges joining them. The optimal solution occurs at some vertex. If the optimal solution is not unique, the optimal points lie on an edge. These observations are also true for the general linear programming problem. Thus, our problem is to find that particular vertex of the convex region which corresponds to the optimal solution. The most commonly used method to obtain the optimal vertex is the simplex method. In this method, we move step by step from one vertex to the adjacent one. Of all the adjacent vertices, the one giving better value of the objective function over that of the preceding vertex is chosen. This method of jumping from one vertex to the other is then repeated. This method then yields the optimal vertex in a finite number of steps, since the number of vertices is finite. Suppose there are m constants and m plus n variables, m less than or equal to n, then the starting solution is found by setting n variables equal to 0 and then solving the remaining m equations, provided that the solution exists and is unique. The n 0 variables are called non-basic variables, while the remaining m variables are called basic variables, and they form a basic solution. So, in a linear programming problem, the variables must always be non-negative. This is very important. In a linear programming problem, the variables must always be non-negative. If a basic solution contains negative variables, then it is called a basic infeasible solution and it is not considered. To achieve this, we start with a basic solution which is non-negative and then use feasibility condition to obtain the next basic solution. Such a solution is called basic feasible solution. If all the variables in the basic feasible solution are positive, then it is called non-degenerate solution. If some of the variables in the basic feasible solution are 0, we will call it as a degenerate solution. A new basic feasible solution is obtained from the previous one by equating one of the basic variables to 0 and replacing it by a new non-basic variable. The eliminated variable is called as the outgoing variable, while the new variable is called as the incoming variable. Okay, so, to obtain a new basic feasible solution, we equate one of the basic variables to 0, replace it by a new non-basic variable, and then the eliminated variable is called as the outgoing variable. The new variable that comes in is called as the incoming variable. Now, the incoming variable must improve the value of the objective function, which is ensured by the optimality condition. The process is repeated till no further improvement is possible. The resulting solution is called the optimal basic solution or simply optimal solution. The simplex method is therefore based on two conditions: feasibility condition. Feasibility condition ensures that the starting solution is basic feasible. The subsequent solution will also be basic feasible. The optimality condition ensures that only improved solutions will be obtained. Now, say for example, let us consider the general linear programming problem: maximize z equal to sigma j equal to 1 to n c j x j, that is c 1 x 1 plus c 2 x 2 and so on c n x n. Subject to the constants, the equations sigma j equal to 1 to n a I j x j plus s I equal to b I equal to 1 to m and x j greater than or equal to 0, s I greater than or equal to 0, j runs from 1 to n, okay, and I goes from 1 to m. So, here you can see the constants sigma j equal to 1 to n a I j x j less than or equal to b I has been converted into equations by using the slack variables s I, okay, because when we have sigma j equal to 1 to n a I j x j less than or equal to b I equal to 1 to m, we can convert them into equations by adding slack variables. So, sigma j equal to 1 to n a I j x j plus s I equal to b I, where s i's are greater than or equal to 0 for all I. So, these are select variables which are used to convert the m constants into equations. Now, so this is our general linear programming problem. Maximize z equal to sigma j equal to 1 to n c j x j, that is C 1 x 1 plus C 2 x 2 and so on C n x n, subject to these m equations, where x j's are greater than or equal to 0 for all j and s I are greater than or equal to 0 for all I. Now, x 1 x 2 x n is a solution of the linear programming problem if it satisfies the constants. So, x 1 x 2 x n will be called as a solution of the linear programming problem if it satisfies these constants sigma j equal to 1 to n a I j x j less than or equal to b I for all I equal to 1 to and so on up to m. Now, this solution will be called a feasible solution of the general LPP if it satisfies both the constants and the non-negativity restrictions. So, if x 1 x 2 x n satisfies the constants, these m equations together with x j greater than or equal to 0 for all j equal to 1 2 and so on up to n, that is they are non-negative and they satisfy these m constants constant equations, we will say that x 1 x 2 x n give us a feasible solution. Okay. So, x 1 x 2 x n will be called a feasible solution of the general LPP if it satisfies both the constants and the non-negativity restrictions. Now, the set S of all feasible solutions is called as the feasible region. Okay. Now, it is the basic solution, it is the solution of m basic variables when each of the n basic variables are equal to non-basic variables are equal to 0. So, if you take the non-basic variables say x 1 x 2 x n to 0, then we have m equations involving m variables s 1 s 2 s m. Okay. So, we will be able to get the solution the values of s 1 s 2 s m from these m equations, then x 1 x 2 x n and s 1 s 2 s m will give us a basic solution of the linear programming problem. So, it is the solution of m basic variables when each of the n non-basic variables is equated to 0. Now, basic feasible solution, it is that basic solution which also satisfies the non-negativity restrictions 3. So, basic solution will be called basic feasible solution if x 1 x 2 x n s 1 s 2 s m are all greater than or equal to 0. Now, if optimal solution, it is that basic feasible solution which also optimizes the objective function. So, among all the basic feasible solutions, the one which optimizes the objective function while satisfying conditions 2 and 3 is called as the optimal solution. There will be several basic feasible solutions. Okay. So, among all those basic feasible solutions, the one which optimizes the objective function, okay, will be called as the optimal solution. Now, non-degenerate basic feasible solution. Non-degenerate basic feasible solution is that basic feasible solution which contains exactly m non-zero basic variables. Okay. So, if any of the basic variables becomes 0, then it is called as a degenerate basic feasible solution. So, let us say x 1 x 2 x n we are taking as zeros, then x 1 x 2 x n are basic variables non-basic variables and m 1 x s 1 s 2 s m are called basic variables. Okay. So, s 1 s 2 s m are called basic variables. If any of the basic variable s 1 s 2 s m becomes 0, then the solution will be called as a degenerate basic feasible solution. Okay. In case of a non-degenerate basic feasible solution, s 1 s 2 s m will be non-zeros. Okay. So, it is that basic feasible solution which contains exactly m non-zero basic feasible solution basic variables s 1 s 2 s m must be non-zero. While taking x 1 x 2 s m x 1 x 2 x n equal to 0, the values of s 1 s 2 s m, if they turn out to be non-zero, then the basic feasible solution will be called as non-degenerate. If any s 1 s 2 s m comes out to be 0, then it will be called as a degenerate basic feasible solution. Now, working procedure of simplex method. check whether the objective function. Now, first of all, when we start to solving a problem by using simplex method, we first check that whether the function that objective function is to be maximized or minimized. If it is to be maximized, no, then it is okay. If it is to be minimized, then we will convert to a maximization problem. So, simplex, in the simplex method, first of all the objective function has to be maximized. Okay. So, if it is already given as a maximized z, then we start as such. If it is given as a minimization of z, find minimum value of z, then we will convert it to a maximization problem. So, suppose z equal to C1 x1 plus C2 x2 and so on, Cn xn is to be minimized, then we convert it into a problem of maximization by considering minimize z equal to maximize minus z. So, minimize z equal to minimize z means maximize of minus z. Okay. The right hand side of each of the constants, suppose there are m constants, then right hand side of each of the constants should be made non-negative. If the linear programming problem has a constant for which a negative bi is given, okay, then we will multiply the constant by minus 1 to make the right hand side positive. Okay. So, it should be converted into the positive value by multiplying both sides of the constant by minus 1. For example, suppose the constant is given like this, 7 x1 minus 8 x2 greater than or equal to minus 3, then it will be converted into minus 7 x1 plus 8 x2 less than or equal to 3. So, we have to make this minus 3 and that we can do by multiplying by minus 1. The coefficients of slack variables in the objective function are taken as zeros. Convert all inequalities of constants into equations by introducing slack / surplus variables in the constants, giving equations of the form this. Suppose let us take the first equation. In the first equation we are using slack variable S1, okay. Then the equation will become a11 x1 plus a12 x2 and so on, a1 and xn, then S1 into 1, 0 into S2, 0 into S3 and so on, 0 into Sm. Suppose there are m constants. So, 0 into Sm equal to B1. So, we will use slack variables S1, S2, S3 to convert the given equations into given constants into equations. We might have to use surplus variables also, that we will come later. So, right now we are talking about the slack variable here. So, suppose the constant is like this, a11 x1, a12 x2 and so on, a1 and xn less than or equal to B1. Then it can be converted into an equation by using slack variable S1, a11 x1, a12 x2, a1 and xn plus S1 equal to B1. Okay. We can write it as a11 x1 plus a12 x2 and so on, a1 and xn, S1 plus 0 S2, 0 S3 and so on equal to B1. Now, find an initial basic feasible solution. After the constants have been converted into equations, we start to find a initial basic feasible solution. There are m equations, not n plus m. Suppose there are m equations involving n plus m unknowns. What we will do? We will assign 0 values to any n variables, okay, so that we have m equations involving m unknowns, and then we start with the basic solution for which okay. So, those m equations in m unknowns can then be solved, okay. If a unique solution exists there, then we will find it. So, if suppose there are m equations involving n plus m unknowns, then assign 0 values to any n of the variables for finding a solution. So, when you put n variables as zeros, then we will have m equations involving m unknowns, okay. So, we will then find a solution. Now, starting with the basic solution. So, what we will do? We will choose n variables x1, x2, xn each to 0, okay. We will take x1, x2, xn to be equal to zeros and then find all Si I equal to 1 to m. So, suppose the equations are like this, a11 x1, a12 x2 and so on, a1 n xn plus S1 plus 0 S2, 0 Sm equal to B1. This is first equation. Second equation, a21 x1, a22 x2 and so on, a2n xn plus 0 S1 plus S 2, 0 S 3 and so on, 0 S m equal to B 2, and the last mth equation is A m 1 x 1, A m 2 x 2, A m n x n, 0 S 1, 0 S 2, 0 S m minus 1 plus S m equal to B m. Now, you can see there are m equations, involving n plus m unknowns. Okay. What we will do to obtain basic feasible solution, we will take x 1 x 2 x n equal to 0. Okay. So, we will take x 1 x 2 x n equal to 0, then we will have m equations involving m unknowns S 1 S 2 S m, and we can find the values of these m unknowns. S 1 will be equal to B 1, S 2 will be equal to B 2 and so on, S m will be equal to B m. Now, since we have already made right hand sides of these constants B 1 B 2 B m positive, okay, the values of S 1 S 2 S m will always be greater than or equal to 0. So, we will get x 1 x 2 x n equal to 0, S 1 S 2 S m equal to S 1 equal to B 1, S 2 equal to B 2, S m equal to B m. So, we have x j greater than or equal to 0 for all j, and S I greater than or equal to 0 for all I. So, then the solution x 1 x 2 x n, S 1 S 2 S m, okay, satisfies these m equations, and also satisfies the non-negativity restrictions. Therefore, x 1 x 2 x n equal to 0 and S 1 equal to B 1, S 2 equal to B 2, S m equal to B m, okay, will give us a basic feasible solution. So, if all S I are greater than or equal to 0, the basic solution is feasible and non-degenerate. Okay. If one or more of the S I values are 0, then the solution will be called a degenerate solution. So, if any B I is 0, then the solution will be called degenerate. If no B I is 0, then S 1 S 2 S m will be all positive and the solution will be called a basic feasible solution. So, this is how we find the initial basic feasible solution for the given LPP. Now, let us write this information in the form of this table. Okay. So, here what is C0? C0 consists of C1, C2, C3 and so on this. Okay. So, C1, C2, C3 are the coefficients of A11, C1, C2, C3 are the coefficients of x1, x2 and so on xn in the objective function. Okay. Objective function is this, these are our objective function. So, C1, C2, Cn are coefficients of x1, x2, xn, the decision variables in the objective function. So, coefficient of x1 is C1, coefficient of x2 is C2, coefficient of x3 C3 and the coefficients of S1, S2, Sn, okay, are taken as 0 here. Okay. So, we consider z equal to suppose the problem is minimization, then we will consider maximization of minus z. Okay. So, we will have minus C1 x1 minus C2 x2 minus Cn xn, okay, and then 0 S1, 0 S2, 0 Sn. So, coefficients of the select variables are taken as zeros, okay, and coefficients of x1, x2, xn are taken as minus C1, minus C2, minus Cn if the problem given is of minimization. If the problem given is of maximization, then the coefficients of x1, x2, xn will be C1, C2, Cn and coefficients of S1, S2, Sn will be zeros in the objective function. So, here we are taking the coefficients of x1, x2, xn as C1, C2, Cn, that means we are assuming that the problem is of maximization, and then S1, S2, Sn, the coefficients of S1, S2, Sn are taken as zeros. Okay. And then the variables x1, x2, xn are the non-basic variables, S1, S2, Sn are the basic variables. So, under the basis we write the variables S1, S2, Sn and their coefficients in the objective function are zeros. So, we write 0, 0, 0 and so on. Okay. This is body matrix, this is body matrix. Okay. A11, A12, A13 and so on, A1n, A21, A22, A23, A2n, A31, A32, A33, A3n. So, that n by n matrix is the that m by n matrix, not because we will have here we are having m equations. Okay. So, we will have m equations we have. So, A11, A12, A13 and so on A1n, A21, A22, A23, A2n, A31, A32, A33 and so on A3n. These are the coefficients of x1, x2, xn. Okay. They form the body matrix, and the coefficients of S1, S2 in the first equation, coefficient of S1 is 1, coefficient of S1 is 1, coefficient of S2 is 0, coefficient of Sm is 0. So, we write 1 0 0 0. Okay. And then in the second equation, coefficient of S1 is 0, coefficient of S2 is 1. So, we get 0 1 0 0 and so on. So, we get 0 1 you see 0 1 0 0 and so on. Then in the third equation, the coefficient of S1 is 0, coefficient of S2 is 0, coefficient of S3 is 1. So, we get 0 0 1 and so on. Okay. So, and then this is B column. In the B column, we write B1, B2, B3 and so on. Okay. The right hand sides of the constants. So, this is how we find the first simplex table. Now, the variables S1, S2, S3 here, the variables S1, S2, S3 are called as the basic variables, and the variables x1, x2, x3 are called as the non basic variables. Basis refers to the basic variables S1, S2, S3 and so on. Cj row denotes the coefficients of the variables in the objective function. Cb column denotes the coefficients of the basic variables only in the objective function. Okay. So, in the Cb column we write the coefficients of the basic variables only in the objective function. The B column denotes the values of the basic variables while the remaining variables will be always 0. Okay. So, in the B column we get the values of the basic variables while the remaining variables are always 0. The coefficients of xi's, that is decision variables, in the constant equations constitute the body matrix. So, you see here this body matrix, the coefficients of xi's, these decision variables x1, x2, xn, they are the decision variables, their coefficients constitute the body matrix. The coefficients of x1, s2, s3 and so on, okay, they constitute the unit matrix 1 0 0 0 0 1 0 0 and so on. You see here 0 0 0 1. Okay. This m by n matrix, m by m matrix, because we have m rows and we have m columns here S1, S2, Sm. So, this is m by m matrix, while this body matrix is m by n matrix. So, body matrix has got m rows and n columns, A11, A12, A1n, A21, A22, A2n, and we have AM1, AM2, Amn. So, this is body matrix and this is unit matrix. Okay. So, select variables, okay, coefficients of select variables constitute the unit matrix. Now, optimality test. Okay. So, we will compute Cj, okay, capital Cj equal to a small cj minus Zj. What is Zj? Zj is sigma Cv Aij. Cj row is called the net evaluation row and indicates the per unit increase in the objective function if the variable heading the column is brought into the solution. Okay. Now, if Cj is less than or equal to 0 for all j, okay, then the initial basic feasible solution is optimal. So, this is feasibility condition. This is optimality condition. If Cj is less than or equal to j, if Cj is less than or equal to 0 for all j, this is called feasibility condition. So, if Cj is less than or equal to 0 for all j, then the initial basic feasible solution is optimal. If even one Cj is positive, then the current feasible solution is not optimal and we will proceed to the next step. It has to be improved. So, now if there are more than one positive Cj, okay, if there are more than one positive Cj, then the incoming variable is the one that heads the column containing maximum Cj. Okay. If there is more than one Cj which is positive, then we will take that value, that consider that value which is the maximum, and in that particular column the variable which is heading that column, that will be incoming, while so the column containing it is known as the key column, which is shown marked with an arrow. We will mark it by an arrow like this. Okay. So, we marked with an arrow at the bottom. If more than one variable has the same maximum Cj, any of these variables may be selected arbitrarily as the incoming variable. Now, divide the elements under V column by the corresponding elements of key column and choose the row containing the minimum positive ratio theta. Then replace the corresponding basic variable by making its variable value 0 if it is if it termed as the, it is termed as the outgoing variable. Okay. So, we will consider we will have the key column, the values of V column are then divided by the corresponding values in the key column, okay, and that gives us the values of theta. The ratios will give us the values of theta. We will find the minimum positive ratio theta. Among all the positive ratios, we will take that one which is the minimum positive ratio. So, that then replace the corresponding. So, suppose this is your theta column. Okay. We have here values in the theta column. Okay. We suppose this is the minimum positive ratio, then this row, okay, this row will be called as key row. This row will be called as key row, and we will replace the basic variable, that basic variable here, the basic variable which occurs in this row. Okay. This basic variable will be given value 0, and it will be replaced by the incoming variable which contains the so therefore, suppose the incoming variable is x1, okay, then this is your key column. So, this element, okay, this element will be which element which occurs at the intersection of key column and key row, that will be key element. This basic variable, suppose this is S1, okay, S1 will then be replaced by x1 in the new table, and in the CB column we will write the value of the coefficient of x1 in the objective function. Before this process, the coefficient of S1 will be here in the CB column, but after we have done this we have got the key row and key column, and then this will be incoming variable, this will be outgoing variable, S1 will be replaced by x1, and the coefficient of x1 will be put here in place of the coefficient of S1. So, that will become the new simplex table. So, so this variable will be called as the outgoing variable, this S1 will be called as the outgoing variable, its value is made 0. Now, the corresponding row is called, this row is called the key row, which is shown with by an arrow on its right hand. So, we will be showing it by an arrow on its right hand. The element at the intersection of the key row and key column as key element, this element will be called key element, which is shown bracketed. Now, if all these ratios are less than or equal to 0, suppose that all the ratios here, okay, under theta column are less than or equal to 0, the incoming variable can be made as large as we please without violating the feasibility condition, and therefore, the problem will have an unbounded solution and no further iteration is required. So, if all the values in the theta column turn out to be less than or equal to 0, then the problem will have an unbounded solution, and we do not need to proceed further. Now, we drop the outgoing variable, as I said, we drop the outgoing variable, introduce the incoming variable along with its associated value under CB column. Convert the key element to unity. What we will do? We will after we have replaced S1 by x1, and here we put the coefficient of x1 here in the CB column, we divide the key row by the key element to make it unity, okay, and with the help of this unity here we make the elements in the other elements in the key column zeros using elementary row operations. So, convert the key element to unity by dividing the key row by the key element, then make all other elements of the key column 0 by subtracting proper multiples of key row from the other rows. This is nothing but sweep out process used to solve the linear equations. the operations performed are called elementary row operations. And then we apply optimality test, okay. That is, we find capital Cj. So, this one capital Cj, which is equal to Cj minus Zj, Zj is sigma Cb Aij, and then check whether Cj is less than or equal to 0 for all j. If it is Cj is less than or equal to 0 for all j, then the solution that we have got is the optimal solution. If even one Cj is positive, then the current feasible solution is not optimal, and we proceed to next step. So, go to step optimality test and repeat the computational procedure until either an optimal or unbounded solution is obtained. Okay. Now, let us see how we can solve given LPP using the simplex method. So, let us consider we are given z equal to 40 x 1 plus 35 x 2, and we have to maximize this objective function. So, here we do not have to convert this problem into maximization, because it is already a maximization problem. If it is minimization of z equal to 40 x 1 plus 35 x 2, then we will convert into a maximization problem by considering maximum of minus z, that is maximum of minus 40 x 1 minus 35 x 2, that we would have done. Okay. But here it is already a maximization problem. So, we keep it as such, maximization of z equal to 40 x 1 plus 35 x 2. Now, we are given two constants equations, 2 x 1 plus 3 x 2 less than or equal to 60, 4 x 1 plus 3 x 2 less than or equal to 96. So, we convert these constants into equations by using slack variables. Because there are two equations, so we need two slack variables S 1 and S 2. So, by introducing slack variables, the problem now becomes, now 2 x 1 plus 3 x 2 into 2 x 1 plus 3 x 2 plus S 1 plus 0 S 2 equal to 60. Okay. And the second one we will write as 4 x 1 plus 3 x 2 plus 0 S 1 plus S 2 equal to 96. Objective function will be z equal to 40 x 1 plus 35 x 2 and 0 S 1. Coefficients of slack variables in the objective function are taken as zeros, 0 at S 1, 0 S 2. Okay. So, the problem will become maximize z equal to 40 x 1 plus 35 x 2 plus 0 S 1 plus 0 S 2, subject to the two equations, 2 x 1 plus 3 x 2 plus S 1 plus 0 S 2 equal to 60, 4 x 1 plus 3 x 2 plus 0 S 1 plus S 2 equal to 96, and x 1 x 2 S 1 S 2 are all greater than or equal to 0. Now, we find initial BSF. Okay, initial BFS we find. So, for that we take now there are two equations here, and we have four unknowns, okay, x 1 x 2 S 1 S 2. So, we can find a unique solution if we take any two variables equal to 0. So, we take x 1 and x 2 equal to 0, x 1 equal to 0, x 2 equal to 0, then we get S 1 equal to 60, S 2 equal to 96. So, x 1 equal to 0, x 2 equal to 0, S 1 equal to 60, S 2 equal to 96 is the solution of this LPP. It is a basic feasible solution of this LPP, because x 1 x 2 S 1 S 2 are all greater than or equal to 0. A solution becomes a basic solution if it satisfies the non-negativity restrictions. Okay. So, x 1 equal to 0, x 2 equal to 0, S 1 equal to 60, S 2 equal to 96. They are all x 1 x 2 S 1 S 2 are all greater than or equal to 0. Okay. And therefore, we have found the initial basic feasible solution. Okay. And z will then be equal to 40 into x 1 plus 35, z will be equal to 0, maximum of z equal to 0, because 40 x 1 is 0, x 2 is 0, S 1 is 60, S 2 is 96. So, z gives us the value 0. So, now let us write the first table. Okay. Cj row contains the coefficients of the variables x 1 x 2 S 1 S 2 in the objective function. So, coefficient of x 1 is in the objective function is 40, coefficient of x 2 in the objective function is 35, coefficient of S 1 in the objective function is 0, coefficient of S 2 in the objective function is 0, and x 1 x 2 are your non-basic variables, S 1 S 2 are basic variables. So, we write S 1 S 2 under the column basis. In the column basis we write S 1 S 2. The coefficients of S 1 and S 2 in the objective functions are zeros. So, we write them in the CV column. CV column contains the coefficients of the basic variables in the objective function, and this is body matrix 2 3, okay, 4, 3. Okay. This is body matrix A11 x1 plus A12 x2 less than or equal to 60 were given to us. Okay. This was the equation. Okay. So, 2 3 4 3, okay, 2 3 4 3, this is body matrix, and 1 0 0 0 0 1, okay, that is unit matrix. So, we have this 1 0 0 1, this is unit matrix and this is body matrix 2 3 4 3. Now, what we will do, and this is B column. B column contains the constants B 1 B 2, okay, these B 1 B 2, this one. Okay. Now, what we will do, so we will find Zj first. Zj is sigma Cb Aij. Cb means the coefficients of the values in the Cb column are multiplied by the corresponding values in the x1, x2, s1, s2 columns. So, Cb is so first we multiply 0 0, this is the values in the Cb column to the coefficients in the x1 column. So, 0 into 2 is 0, 0 into 4 is 0. So, total is 0. Okay. So, we get this. So, this sigma Cb Aij means we have sigma Cb, this is obtained from sigma Cb into Ai1, okay, this first column, okay, and I takes values from 1 to 2. Okay. So, this is Zj means Z1, okay, first column. Okay. So, this is Z1, Z1 is equal to 0 into 2 plus 0 into 4, we get 0. So, this is Z1. Now, Z2 equal to sigma I equal to 1 to 2 Cb into Ai2. Okay. So, we have 0 into A12, 0 into A12 means 0 into 3 plus 0 into 3. So, we get 0. So, this is Z2. Okay. Then Z3 means sigma I equal to 1 to 2 Cb into this one A11, A12, A13, you can say this A1, AI3, third column. Okay. So, that is this AI3, that is A13, this is A23. Okay. So, we get 0 into 1 plus 0 into 0 equal to 0. So, we get this. Similarly, we get 0 into 0, 0 into 1 equal to 0. Okay. Now, we then find Cj, capital Cj equal to Cj minus Zj. Okay. So, that means suppose in the first column C1, in the first column j equal to 1, C1 will be equal to C1 minus Z1, and C1 is equal to 40. So, 40 minus Z1 equal to 0. So, we get 40 here. Okay. And similarly, C2 will be C2 minus Z2. So, 35 minus 0, we get 35. So, this is 35, and then here 0 minus 0 is 0, 0 minus 0 is 0. Now, we can see Cj is greater than or equal to 0 for Cj is strictly positive for j equal to 1 and 2. Okay. For j equal to 1 it is 40, for j equal to 2 it is 35. So, we take the maximum value, okay, maximum value is 40. Okay. So, this column is our key column, we show it by an arrow pointing upwards. Okay. So, this is our key column. Now, what we will do in the key column, the elements 2 4, okay, we divide the elements in the B column by the corresponding elements in the key column. So, 60 divided by 2 gives you the value of theta for this first row. Okay. In the second we get 96 divided by 4. Okay. So, this is 30 and this is 24. Okay. Now, both are positive, both values of theta are positive. So, we then find the minimum positive value of theta. This is minimum positive value of theta, and therefore, this is our key row. Okay. So, this is key row and this is key column. okay, and at the intersection of key row and key column we have 4. So, this 4 we have bracketed, this 4 is the key element. Key element is 4. Now, what will happen? This S2 will be outgoing variable and x1 will be incoming variable. So, in the next simplex table S2 will be replaced by x1, okay, and the coefficient of x1 which is 40 will replace this 0 here. 0 was the coefficient of S2 in the objective function. Now, in the objective function the coefficient of x1 is 40. So, 40 will come here, x1 will come here. After that we divide the key row by 4, okay, to make this element which is key element. To make it unity we divide the elements of key row by 4, okay. So, in next simplex table will be CB, and in the CB 0 here we will get 40, in we will get basis S1, and here we will get in place of S2 we will get x1, okay, and then Cj will be 40 as such, okay, 35, and we will get 0 0, all right, and here we will have x1 x2 s1 s2, okay, and we divide it by 4. So, this row will become 1 3 by 4, okay, 1 3 by 4 0 1 by 4, and here we will get 96 by 4, that means 24. This is B column, okay, B column, okay. Now, with the help of this 1, okay, we will make the entries, other entries in the key column zeros. So, there is this entry 2, we will have to make it 0. So, we multiply it by 2 and subtract from this row. So, we will get 0 here, okay, and we multiplied by 2. So, this becomes 3 by 2, 3 by 2 we subtract from 3. So, we get 3 by 2 here, and we multiply 0, we divide 0 by, we multiply this by 2 and subtract from 1. So, we get 1, okay, and here what we get here, we multiplied by 2. So, we get 1 by 2, 1 by 2 we subtract from 0. So, minus half we get here, okay, and here what we will have, 24 is multiplied by 2, we get 48, 48 is subtracted from 60, we get 12 here, okay. So, this is our new table, you can see this one, okay. We have S1 x1 0 40, then 0 3 by 2, 0 3 by 2 1 minus half, 0 3 by 2 1 minus half 12, and then 1 3 by 4 0 1 by 4 24, okay. Now, we find again Zj. So, Zj is sigma Cb Aij. So, 0 into 0 is 0, 0 into 40 into 1 is 40, total is 40. So, we get 40 here, and then 40 minus 40 is 0, and then we get 0 into 3 by 2 0, 40 into 3 by 4, that means 30. So, 30 is here, okay, total is 30, 30 is here, 35 minus 30 is 5, and then 0 into 1 is 0, 40 into 0 is 0. So, we get total 0, 0 minus 0 is 0, okay, and then 0 into minus half is 0, 40 into 1 by 4 is 10, total is 10. So, we get 10 here, 0 minus 10 is minus 10, okay. So, we got the values of Zj, we got the values of capital Cj. Now, we can see Cj is positive, okay, in for j equal to 2 in the second column, Cj is positive, okay. Therefore, we still have not got the optimal solution, okay. So, this is our key column, there is only one positive value, okay. So, this is our key column. We divide the elements of under B column by the corresponding values in the key column. So, 12 divided by 3 by 2. So, 12 into 2 by 3. So, we get 8, okay. We get 8 here, and then 24 divided by 3 by 4. 24 divided by 3 by 4 means 4 by 3. So, we get 32. So, we get 32. Okay. Now, both are positive values in the theta column. So, minimum value will be considered. So, 8 is minimum. So, this is our key row. Okay. At the intersection of key row and key column, we get the element 3 by 2. So, this bracketed element is the key element. Now, what we will do? We divide this row, okay, key row by the key element. Okay. The what we will get? x1, x2, s1, s2, b. Okay. It will, after dividing by 3 by 2, we will get 0, 1, 2 by 3, okay, and we divide by 3 by 2. So, we get minus 1 by 3, okay, minus 1 by 2 into 2 by 3. So, we get minus 1 by 3, and then 12 divided by 3 by 2. So, 12 divided by 3 by 2 means 12 into 2 by 3. So, we get 8 here. Okay. After we have converted the key element to unity, okay, we make the element 3 by 4. This element we have to make 0. So, we multiply it by 3 by 4 and subtract from this row. Okay. So, what we will get? We multiply it by 3 by 4. Okay. 3 by 4 we multiply here and subtract from this. So, this will remain 1 and this will become 0, and this is multiplied by 3 by 4. So, 2 by 3 into 3 by 4. So, we get half. Okay. So, we multiplied by 3 by 4 and subtract from 0. So, 0 minus 1 by 2. So, we get minus half. Okay. And we multiply it by 3 by 4. Okay. 3 by 4 we multiply. So, minus 1 by 3 into 3 by 4. So, we get minus 1 by 4. So, we subtract, after multiplying 3 by 4 to this row, we subtract from the second row. So, 1 by 4 plus 1 by 4, 1 by 2 we will get here, and here what will happen? We multiply by 3 by 4. So, 8 into 3 by 4 means 6. So, 6 we subtract from 24 and we get 18. Okay. And moreover that S1 will be replaced, because this is key row and this is key column. Okay. So, S1 will be replaced by x2 here. So, we will get here 35, here 40, here x2, x1. Okay. So, let us see 35, 40, x2, x1, and 0, 1, 2 by 3, 0, 1, 2 by 3, okay, minus 1 by 3, and here we will have 8, and then 1 0 minus half, 1 0 minus half, and here we will get 18. Okay. So, this is 18, this is 8, okay, this is 8 and this should be 18. Okay. And what we will get then? Yes. So, now we can see we can find Zj, Zj equal to sigma Cb Aij. So, 35 into 0 is 0, 40 into 1 is 40. So, we get 40 here, 35 into 1 is 35, 40 into 0 is 0. So, we get 35 here, 35 into 2 by 3. So, we get 70 by 3, and then we get 40 into minus half. So, minus 20. So, we get 10 by 3. So, we get 10 by 3 here, and then 35 into minus 1 by 3. So, minus 35 by 3, and then we get 40 into half. So, we get 20. So, we get 60 minus 35. So, 25 by 3. So, we get 25 by 3 here, and then 40 minus 40 is 0, 35 minus 35 is 0, 0 minus 10 by 3 is minus 10 by 3, 0 minus 25 by 3 is minus 25 by 3. Now, Cj is less than or equal to 0 for all j, and therefore, the above solution is optimal. So, what we get? We get x1 equal to 8, x1 equal to 18, okay, x1 equal to 18 and x2 equal to 8, x2 equal to 8, and the value of z will be 35 into 8. Okay. So, we find Cb into we have z equal to x1 40 into x1 plus 35 into x2, that is z. Okay. x1 is equal to 18. So, 40 into 18, okay, 40 into 18 and 35 into 8, that is we multiply Cb column, okay, by B column. So, 35 into 8, okay, and then 40 into 18. So, this is 720 plus, so 720 plus 280. So, that is 1000. So, z is equal to maximum value of z equal to 1000. Okay. So, that is how we solve the given linear programming problem. In our next lecture, we will discuss some more examples on simplex method, where we will find unbounded solution. Here we found a optimal solution. In those problems we will find unbounded solution. So, that we will do in our next lecture. So, thank you very much for your attention.